Right, and welcome to this lesson. This is the second and last lesson on the solubility equilibria one. And what we're going to be doing now is doing some more calculations, the last two different types, and then the type of explanation type questions you can be asked. So it's a common ion effect, calculations involving the common ion, ionic product, that's another type of calculation with a predicting precipitation. And then the complex ions and the effect of pH are some of those explanation type things that you need for merit and excellence. So this is what we looked at last week. When you look at your sparingly insoluble salt, like calcium carbonate or calcium sulfate or something like that, it's much easier if we try and break it down into an AB salt or a A2B or a AB2. So if you were here with last week, as I think you were, then you wouldn't have a problem. I'm not sure if the two Catherines are different. So just as a comparison, if I had calcium sulfate, what type of salt would calcium sulfate be? AB, A2B, AB2. This is also checking if you know your ions. Does anybody want to have a go? AB, correct, because it's 1 calcium to 1 sulfate, because it's calcium 2 plus and SO4 2 minus. If I had silver sulfate, what type of salt would silver sulfate be? A2B, correct, because it's Ag2SO4, because the charge on a silver ion is Ag plus, the charge on sulfate is 2 minus, so I need 2 silvers for 1 sulfate. And that's, as I say, important in terms of the amount of then the particular ions that are formed. So I need 2 silver ions to 1 sulfate, and that'll affect then, I'm missing a square bracket here for some reason. That'll affect my solubility constant expression. Remember, this whole equation is what we call an expression, solubility constant expression, and the solubility product is this value given by Ks. And if I have an AB salt, it's a straightforward, we just either square it or take the square root, depending on if we're getting this calculating the solubility or the solubility product. And this shortcut will only work in pure solutions. In other words, the only source of my silver ions and or in this case calcium sulfate, the only source of calcium ions and sulfate ions are from the calcium sulfate that I've added. So this is just a revision from last week, and then if I have an A2B or AB2, then I have this 4s cubed, or I take the cube root of Ks divided by 4. Now I've gone over that very quickly because I'm summarizing from last week. Are there any questions on that? So Catherine, I'm not sure if you've seen this last week, if you were the same Catherine, or a different one because it's different spelling. Are you okay? Okay, I just see you typing. So just while it's typing, I'm going to the next slide, but just carry on there. These are the 4 calculations you will be asked in the exam. You'll be asked at least 2 of these. Okay. Okay, right, so I'm just going back to what Catherine said there. Fine, so that's just a summary of what we did last week, but we'll be repeating some of that this week, so don't worry too much if you get a bit lost, or if you get a bit lost, just please ask questions in that chat box. So the number 1 and 2 is what we covered last week. This is the straightforward calculating the solubility product, where we give you a concentration. We normally give you the solubility and say work out the solubility product. Or number 2 is we give you the solubility, we give you the solubility product and ask you to calculate the solubility. So it's the opposite. And these are normally done in a pure water, pure solution, so the only source of the ions is from my substance, like silver sulfate or calcium sulfate. The only way they can make these more tricky is, instead of, say, giving you the concentration of a substance, like I've said here, at least one concentration must be given, they might give you the mass and the volume, and they'll expect you to work out the concentration yourself. So it's just a few more steps. So what we're going to do today, though, is we're going to look at what happens when we need to calculate the solubility with a common ion, and I'll show what that means. And then the other calculation is where we predict the precipitate will form, and then we don't talk about a solubility product, we talk about an ionic product. And these 2 points down here I will explain when we get to that. Okay, so first thing is revision from level 2. Do you remember Le Chatelier's principle? Okay, yes for Catherine and Andrew. Well, we will be going over it. So first of all, great. So first thing is equilibrium. What do we mean by equilibrium? I've given, like here, a seesaw with a system at equilibrium. Does it mean I've got equal amounts of silver chloride to silver and chloride? So have I got equal on this side in terms of amounts and equal amounts on that side? Because I know that seesaw can be, okay, you're saying equal products and reactants. Not quite that, okay? I don't have to have exactly the same amount of products as reactants. What I do have equal and exactly the same in an equilibrium is the amount changing forward is the amount changing backwards. So for every one of these going and changing to the ions, I've got one each of these two going back. So the rates are equal. So I could have lots of these and little of that, but as long as the exchange backwards and forwards is the same, my system is in equilibrium. Okay, exactly where this thing lies is the size of that Ks. So what I'm just trying to show now is, if my rate forward and my rate reverse is the same, it's in equilibrium. And if I try and change that, then the equilibrium position is going to shift to minimize that change. So, and that's really what Le Chatelier's principle is. He was the chemist, French chemist, that first came up with it, that recognized it. So let's give an example here. My system was in equilibrium. I had a bit of silver chloride in water and a tiny bit dissolved, and the amount that dissolved equaled the amount that precipitated out. So that video I was showing last time about how things dissolve, you can just imagine water molecules going around to the corners of the silver chloride, extracting a few silvers and chlorides, but at the same time somewhere else in the solution some silver ions is colliding with some chloride, or is colliding with a solid and is coming out again. So my exchange is equal there. Now say I change something in the system. Say I add a whole lot of water. If I add a whole lot of water, it means I've diluted my concentrations. So my change is I've changed my concentration. So I've made it like go up as though it's lighter. So now I've got, if you like, fewer silver ions and chloride ions in the water, because my concentration is less, because I've dumped in a whole lot of water. What do you think is going to happen, and the arrow sort of shows, when I've added a whole lot of water? Do you think more silver chloride will dissolve or less silver chloride will dissolve? More will dissolve, correct. Because if I make my stress is, or my change is decreasing the ion concentration, so in order to minimize that change is, so as I'm taking away, I've got to add on to try and keep this sort of amount constant. So this, the equilibrium position is going to shift, so my silver chloride will start dissolving more and more. What do you think will happen if I start evaporating the water, so my concentration of silver ions and chloride ions increases because I'm removing the water? What do where do you think, am I going to get more silver chloride being formed or less silver chloride being formed? More. So it's just going to go backwards because now I'm going to shift the seesaw the other way around. So what I'm trying to show here is, so we've done the way we've just added and removed water by changing the concentration that way. But we don't have to just change the concentration of both the silver and the chloride. We can change things by adding, say, more silver ions or more chloride ions. So here I've got a system in equilibrium. So here's my solid. Now all I've done is these particles, these silver ions and chloride ions, would have been floating around in here in my solution, but I've separated them. So I've made those the reactants and those the products. In a beaker, it would all be in the same beaker. And I've made a Ks value where I've said if this is 1 liter and each of these stands for a mole, I've got 2 moles of silver ions and 2 moles of chloride ions. So 2 times 2, so my equilibrium constant would be 4 in this hypothetical example. In real life, it's something like 1.5 times 10 to the minus 9 or something. I don't know it off by heart. But it's in equilibrium. Now, I'm going to show it again, but I've added now a whole lot of silver. So I might have added silver nitrate to my solution. So my chloride ions haven't changed, okay? But my silver ions have changed. So what do you think is going to happen to try and minimize that change? So my change is adding more silver ions. So what will now happen? Will I get more silver chloride being formed, or will I get less silver chloride? Okay, Andrew, you're sort of saying I'm going to get less of that because are you trying to think we've got to try and balance the chloride? Because that could be, okay, yep, that's a sort of common error. What's going to happen though is I've got to keep my Ks constant, because remember that the solubility product has to be the same. So I've got to keep this, my silver ions, because at the moment, can you see I've got 1, 2, 3, 4, 5. I've got 5 times 2. Can you change it's from 4 to 10 now? So my Ks is now 10. So I've got to get rid of some of this to make sure my Ks stays 4. So one way I can do it is say, okay, if I remove some, I've added the silver, so that's the stress of adding silver, so I've got to remove the silver. So the only way it can get removed is by precipitating out. So if I remove the silver, so there's a chloride and there's a silver, because remember if I go backwards, I have to take a silver and a chloride both. I can't just remove the silver. I just can't keep on adding silver to the side. I've got to take a chloride and a silver over. And now if my system's in equilibrium, I know it's in equilibrium because can you see my Ks has stayed the same. I've now got 4 silver ions, 1 chloride ion, but 4 times 1 is 4. Can you see my Ks, my solubility product is the same? I mean, I chose it, so it worked very nicely like this. Remember, of course, in solution, you've got millions and millions and trillions of these ions in solution. So that's really what is happening. If I add any extra ion, it's going to shift to try and remove that ion. And a way we can look at it is, so for Ks to stay constant when I'm increasing the Ag+, then I've got to decrease it because that's my shifting to remove that stress, okay, or change. But of course, if I decrease my Ag, I'm also going to be decreasing my chloride. So note that both of those do get decreased. Okay. So now let's use that understanding to do these calculations. And you also need that understanding and explanation. this is what we had last time. It's a way of making sure you minimize your errors. So remember, always write your solubility equation first. Remember the silver chloride going to silver ions plus chloride ions. Then your expression. So Ks for silver chloride is equal to the concentration of silver ions times the concentration of the chloride ions. And then you start substituting and so on. And just as a final point, the one we had on that second slide of Ks is equal to S squared, we can't use if we have ions from two sources. So remember when I added silver nitrate, that's the common ion. I've added silver but from a different source. So I can't use the shortcut whenever I have a common ion. So here's an example. Calculate the concentration of barium ions which will dissolve in 1 mole per liter of potassium sulfate. Now remember in the last lesson I said if you know your solubility rules, it makes things so much easier because you'll know immediately, barium sulfate insoluble, I've got to calculate for barium sulfate. But all is not lost if you don't know your solubility rules, but I really suggest you learn them. If whenever you're given a Ks and they give you, they have to always say what the Ks is for, the solubility product, that is always a tip of what you've got to go for. So if you see this, calculate the concentration of barium ions, potassium sulfate, and you're going, do I write K2SO4 goes to 2K plus SO4 2 minus, or how do I start? Look at the Ks and that'll give you a clue. Okay, if you knew your solubility rules, you would automatically think of barium sulfate because you know it's insoluble. Okay, all sulfates are soluble except for barium sulfate, lead sulfate. Silver sulfate's fairly insoluble, but I don't think that's in your list. Now what I've got here is, I didn't use this last week, although it is in the book right from those, what I call simple calculations, is what is known as the ICE method, ICE. So initial, change, end. So in the beginning, in the initial, if you think of, I've got my solution of potassium sulfate, and I'm going to be adding barium to it. So there's it's just easier to always start off with lots over here because you know that that's a sparingly soluble salt, so it's going to always be, you know, you never bother working this one out. I think that's the best way of doing it, and then I won't get it involved there. But in the beginning I only had potassium sulfate, so I've got 0 barium, and I know my concentration of sulfate because I was given 1 mole per liter potassium sulfate. And remember, for every 1 potassium sulfate, I have 1 sulfate. So I know my concentration of sulfate is 1 mole per liter. Now, when I add some barium stuff in there, okay, and I want to know how much will dissolve, okay, the X is going to dissolve, but I'm also, that barium has to be also be associated with the barium sulfate. So any barium sulfate I've got will form barium and 1 sulfate. So if that is dissolved, I'm going to have 1 barium, X, because I don't know exactly how much, but I've got to have the same X amount for the sulfate that dissolves. So in the end, when it's all reached equilibrium again, okay, I can still ignore this barium sulfate because it's my insoluble salt and it doesn't affect anything. I've got X amount of the barium that has dissolved, okay, and the amount of sulfate I've got is the stuff from the potassium sulfate plus the X from the barium. So that's where my 2 lots come in, okay, my common ion, the sulfate comes from the barium sulfate as well as from the potassium sulfate. Now, we want to try and keep calculations as simple as possible, and at level 3 you will get ones where you can do assumptions. So what I've got here is I'm going to assume, and you must write this down, you assume my sulfate concentration is still going to be 1 mole per liter, because the K is so small. If I add X to 1, it's still going to be pretty much 1. And when we do with in this red square, we're going to calculate the solubility of barium sulfate in pure water, and it's like 1 plus 0.000000001. And I hope you can see from your just significant figures, if I added that up, can you see it's still going to be 1? Do you think my assumption is pretty valid? Yep. Okay. So state your assumption whenever you've worked out. So you've done that first E. Remember, always stands for equation. Now we're going to do the expression. This is the EQ method in red here. Okay. So there's my expression, and so now I just simply substitute. So I've done my assumption. I'm going to say, okay, KS I've been given. X is that over there. I don't know it, and I've got to calculate it. It says calculate the concentration. And the sulfate I've assumed is going to be 1. So now I just simply solve for X. So if I've got X on this side, I multiply both sides by X. So X, well, easiest is to take the 1 across. So if 1 is being multiplied here, it has to be divided on the other side. But of course, if you divide by 1, it doesn't make any difference. So my X amount, my concentration of barium, is 1.5 times 10 to the minus 9. So that's a fairly straightforward one, as long as you've made the assumption. Now, if you want to see the difference between the effect of that sulfate to when it would be dissolved in pure water, so you wouldn't have to do this calculation in an exam. This is just to show what happens. In pure water, we can use this Ks is equal to S squared, so we can simply take the square root of the solubility product, and if we do that, it's 3.87 times 10 to the minus 5. Can you see that this value is a lot bigger by 10,000 times compared to that? Because this is 10 to the minus 9, that's 10 to the minus 5. Can you see how much more insoluble barium sulfate is when there's a common ion present? Okay, so we'll carry on to the next one. This is another one, just about exactly the same. It's just I've made a 0.1 solution, and I'm using potassium chromate. And if here I've said calculate the solubility of silver chromate, so we know we've got to go silver chromate, and remember I said always look for the solubility product, and what's given, it's silver chromate. So we know that's what we've got to go for, and so the first equation we have to write is always the silver chromate. Silver chromate solid goes to 2 silver ions plus the chromate ion. Now again, we can ignore this side. When you do 306.2, the side gets more important when we do acids and bases, but it's not important in the solubility ones. But what I'm trying to say, in the beginning, I don't have any silver ions, but I do have chromate ions, because I've got a 0.1 mole per liter solution of potassium chromate. So there's I've got 0.1, and the reason why it's 0.1 is for every 1 potassium chromate, how many chromates have I got? 1. So for every 0.1 potassium chromate, I've got 0.1 chromate. And it's the same sort of thing. When I now want to check the solubility, I've got 2x dissolving, okay, or 2x being formed, and I've got x of chromate being formed. So I've got 0.1 plus x. Now look at that Ks value. Is that a very small value or a big value? very small, which means potassium chromate is not very soluble at all. So my next step is the assumption. I can say Ks is so small that quite frankly that X is so tiny compared to 0.1, I'm just going to say chromate is 0.1. And so now there we write the solubility product expression and we just simply substitute. So the 2x gets substituted. So remember that x we now double and square. Can you see the 2 in green is because we form 2x, and that 2 in blue is because when we write the expression, any coefficient becomes, because we say silver times silver, it becomes silver squared. So it gets raised to a power. And the chromate is easy because we've assumed it's 0.1, so it gets in there. And now we solve for x. Now, as I say, I suggest you first have the 4x squared on one side and then work out the other figures. So bring that 0.1 over by dividing it. Divide both sides by 0.1, so you get this value. And then divide that by 4 and then take the square root. A lot of students make an error of taking the square root first and then dividing by 4. You have to divide by 4 first and then take the square root, and that's your answer. Now, I know at the last time I said have your calculators handy, but I never actually sort of stopped and said do this calculation. So try and do the calculation on your calculator and see if you get the same values as what I do. And if you don't, you can ask me, because I may have made an error. It's totally possible. Or it may be that you've not done something correctly in your calculator, because it's very easy to make careless errors. So try this one now where we try it in pure water, just to see as a comparison. So it's an A2B salt. So we use this 4s cubed one. So remember, divide by 4, take the cube root, and I get 9.09 times 10 to the minus 5. So not a great big difference in solubility between pure water and potassium chromate. But can you see this number, 10 to the minus 5, is bigger than that? So it is more soluble in pure water than it is with a common ion. Right. Do any of you want to actually try that calculation with your calculator, or you'll just do it as I go? Okay, I see Catherine's typing. And later on, if you're watching the recording, you can try it. You've done it. And you got the same answer, Catherine? Yep. Okay, great. Now here's another one that you could be asked. Calculate the solubility of potassium fluoride. So what I'm doing in each case, I'm trying to change an AB to A2B to AB2, and I'm also changing other things around it. So here now it's where the anion is the common ion. It's been nearly in every case, but you'll see that the change here now. So I've got potassium fluoride, the Ks, although I haven't got potassium fluoride, calcium fluoride, although I haven't got calcium fluoride written here, the very fact that it's straight after the calcium fluoride means this relates to that. And there is my common ion of fluoride. So start with the equation, and I've got 2 fluorides. So in the beginning I've got no calcium, but I do have fluoride of 0.1 from the sodium fluoride. Be very careful, because I couldn't give all the range of examples, but if I had no, this is going to be a 1-to-1, but sometimes you might have to multiply this value by 2 if it gets, okay, let me go back to the previous slide. Okay, say the common ion was potassium, for example. Then for 0.1 mole per liter of potassium chromate, can you see I've got 0.2 moles per liter of potassium, and 0.1 moles per liter of chromate. So say the common ion was potassium, then you would, in your assumption, you'd have to say it would be 0.2 because I've got twice as much potassium. Does that make sense, or have I now confused you? Okay, deathly silence. So we'll just go and we'll be doing some extra examples as well. Right. Okay. So we've got potassium fluoride, calcium fluoride, sorry, and I've got two fluorides being formed. So in the beginning, my fluoride comes from the sodium fluoride, so it's 0.1. Then, say my potassium fluoride, calcium fluoride is going to dissolve. So for every one calcium fluoride that dissolves, I get one calcium and two fluorides. So at the end, when it reaches all equilibrium, then I've still got lots of potassium fluoride undissolved, calcium fluoride undissolved. I've got X amount of calcium ions, and I've got 0.1 plus 2x of the fluoride ions. But again, look at this Ks. If that's very small, I can ignore the 2x. Correct, Andrew, it's small. So I don't have to worry about that 2x. I can say assume the fluoride is 0.1, and I can ignore the 2x. It will come in though, that 2, because remember I have to square it, because my solubility product expression is calcium times fluoride, because I've got two of them. So it's calcium fluoride squared. And so now I substitute. There's my given value for my solubility product. There's my X for the calcium. And then I just substitute for the fluoride and I square it. And then I solve for X. So try this in your calculator and see if you get that value. And again, if you're not too sure, try it out step by step. So you'll see there 0.1 squared is 0.01. So I've worked that out first before I divided the 4 times 10 to the minus 11 by that value. And if I worked it out in pure water, can you see the difference? It is a lot more soluble in pure water than it is in sodium fluoride. Very little will dissolve in sodium fluoride of 0.1 mole solution, whereas, you know, a fair amount does in pure water. I mean, it's still a tiny amount. It's 0.0002 moles per liter, so not very soluble at all. Okay, right. Okay, Andrea sees typing, but we can go back if it relates to the previous slide. Yes, thank you, Andrew. That's a thing I want to hit home, is that if you add a common ion, it's going to be less soluble, because as I tried to show in that first thing with the silver and the chloride ions moving over, I'm going to get more precipitation. Now, this is what we use when we're trying to predict whether something is going to precipitate or not. We have two terms, ionic product and solubility product. They're exactly the same, except solubility product always applies to an equilibrium. So if it's an equilibrium, it has to be a saturated solution, because I've got to have my solid there in equilibrium with my ions. Okay? If it's not an equilibrium, then, or could even be an equilibrium at any other case, my ionic product, because ionic product just simply means multiply my products. So it's my silver times my chloride. And we can use either IP for ionic product, or you could use Q. So you may see in some YouTube clips or so on, if you're looking on the web, you'll see Q, and that's because that is a symbol for it. New Zealand, I see they tend to use IP. I've stuck with IP because I think it's sort of like easier, ionic product, okay, but Q also means the same thing. Right, so let's take our lead chloride. There's my equation for it, and so if that salt is in equilibrium with its ions, I'd write the expression like this, and that would be the solubility product expression. But my ionic product expression, can you see, is identical. So it's exactly the same, and the only difference is that this one's definitely in equilibrium, this one does not have to be in equilibrium. Okay, so where does this lead us? Is if my Ks is in equilibrium, okay, then I'm going to, by calculating the ionic product, which is when it's not at equilibrium, I can see which way is the reaction going to go. Is it going to go towards the left to form more solid, so I get a precipitate, or is it going to go to the right to form more ions, so I'm going to have less precipitate? Or if I had no precipitate to start off with, I'm going to have even a smaller chance of getting a precipitate. Okay, so what you have to basically know is if the IP is less than the Ks, you don't get a precipitate, but if the IP or the ionic product is more than the Ks, then you will get a precipitate. So I hope this is clear enough to see. Okay, here I've got my solid going to aqueous. If my IP is smaller, that when it's going to try to reach equilibrium, remember when an ionic product is smaller, the equilibrium is lying to the left, or the position of the, I've got less products, more products, because IP is smaller. So it's going to, when it reaches equilibrium, it's got to try and go forward to reach equilibrium. So I'm going to get more ions being formed. But if my ionic product is bigger, then I've got to try and get rid of those ions to reach equilibrium. So I'm going to get a precipitate being formed. So if you're not quite sure how, you haven't got this sort of in your mind, as long as you remember if IP is smaller, you don't. So if this is too small, you don't get a precipitate. If it's big, you do get a precipitate. And if you can think of a nice mnemonic to remember that, that's great, and you can tell us as well. So here's an example. Will a precipitate of calcium carbonate form when I have 1 gram of solid sodium carbonate, and I add it, so it's to a 250 ml solution of this concentration of calcium. So here I've got 2 different solutions. I've got a sodium carbonate solution and I've got a calcium ion solution that's obviously soluble. So it's saying when I mix them, I'm going to form calcium carbonate. But will I form enough calcium carbonate that it's going to precipitate, or won't it? That's really what we're saying. So what we do is, first of all, if you're not sure what the precipitate is going to be, the Ks is always a clue. Okay. And if you know then what the insoluble salt is, you always write that equation first. So you just look for the Ks and you go, oh, they're talking about calcium carbonate. So always write the equation for calcium carbonate first and then the expression. That EQ method, equation, expression, and then you start your calculation. Now with this sort of thing, I always suggest you write a list where you have the ions separated, the calcium ions and the carbonate ions separated from the given value. So I've highlighted here in green that you get for the carbonate ions. So my carbonate I know is 0.1 grams of the sodium carbonate, and I know my molar mass of the sodium carbonate is 106. The ones in blue apply to both because I've got a volume of 250 milliliters of, when I've added this, the carbonates, the volume's still going to stay the same, but the calcium, the only thing I know about that is that concentration. So there I go, I list that. When I've done that, remember I've got to substitute into this expression. Okay, I know it's Ks and I'm going to be using an IP, but it's pretty much the same thing. So I'm going to need the calcium ions and I'm going to need the carbonate ions. Now the calcium ions are easy. I've already been given them. I don't have to do much more. How can I calculate my carbonate ions to plug in there? All I know about the carbonate is I've given a mass, I'm given a molar mass, and something that applies to both is a Ks and a V. So what equation can I use that will eventually lead to a concentration for the carbonate, given what I know in green, mass and molar mass? Okay. N is equal to C over V, correct. I will be using that because I've got to get that concentration, and I've got a V, but I don't have an N. Now, in my units, I have a mole there somewhere, so how can I manipulate this? Correct. So I can manipulate this by saying N is equal to small m over big M. Use your units to help you. Grams divided by grams per mole. Mole at the bottom, per mole at the bottom becomes mole at the top. And once I know N, I can use N is equal to C over V. So there it goes, N of carbonate, and you can do this on your calculator at the same time. And so I can work out the concentration of carbonate. Okay, now notice what I did with my volume. And I should perhaps have put the units in here. You were given 250 milliliters, but a concentration is moles per milliliter or moles per liter. Moles per liter. So when I can't use milliliters and moles per liter, my units aren't going to cancel out. So I always have to change my volume to liters. And the easiest way is just to say, okay, I've got 250 milliliters, so times it by 10 to the minus 3. So you just go in your calculator, exponential 3 minus, and then you've got it in liters. So instead of saying, okay, 250 milliliters is it 0,0025? Is it 0,25? Is it 2,5? Okay. I find that students tend to make fewer errors if they just simply go times 10 to the minus 3 than if they actually physically divided by 1,000 and then wrote a value down. Because every time you write a value down, you're going to perhaps get a transcript error. Okay, so there we get 3.77 times 10 to the minus 3 moles per liter. So I've got now a calcium ion concentration. I've got now a carbonate ion concentration. So now I just simply calculate the IP, or this could have been Q, does the same thing. So it's identical to the Ks expression, except you don't call it Ks. And so there I plug in my calcium ions, my carbonate ions, multiply them together, and now I compare the 1.13 times 10 to the minus 5 by 4.50 times 10 to the minus 9. Now don't be tricked by the numbers in front here, 4.5 and 1.13. 4.5 is bigger than 1.13, but that's not important. What's the important figure that I've got to look at? Okay, not sure? This times 10 to the minus, because that tells me how many numbers I've got. So this number is actually 0.000000004, whereas this one is only 0.000001. There's fewer zeros in front of the number. So which of these is bigger, the Ks or the IP? Okay, the IP is bigger. And because the IP is bigger, the equilibrium is going to shift, because it's, remember, an IP means it's not an equilibrium. So which way is the equation going to go? Perhaps I shouldn't use the word equilibrium shift. Which way is the equation going to go to try and reach equilibrium? If IP is bigger, it means I've got more products. Okay, so the bigger IP, the bigger this has to be. So if I've got more of this, I have to shift to the left to try and make this smaller so this can eventually equal the Ks. Because the RP eventually has to, the reaction is going to do something, so eventually my RP is going to be equal to my Ks. So the only way I can make this smaller is by shifting the calcium and the carbonate ions across to the solid. So by shifting across, can you see a precipitate will form? So Andrew, I know you said they will dissolve, but can you see now why it will form? So if the RP is bigger, I'm going to get a precipitate. Okay. Right, here's another one, and this is from last year's exam. Sample of seawater has a chloride ion concentration of that much. Okay, so you know the chloride ion's concentration. Determine whether precipitate of lead chloride, and you go, aha, that's my equation I've got to use when a 2 gram sample of lead nitrate is added. Now, there they give you a molar mass of lead nitrate, but if you want to work out what insoluble salt you're working at, always look for the equilibrium, the solubility product. Okay, so the opposite clue. So EQ method, always equation first. So find out which one it was. It's lead going to 1 lead ion and 2 chloride ions, and then you write the solubility product expression. Okay, because you'll get your RP from that, because they're exactly the same. And now you look at all your values, highlight them, circle them, do what you like, just to link what comes from the lead, what is for the chloride, and what's for both. So there it is, the chloride's in green, and the lead, what we know about the lead is in orange, and the blue, and I've done straight away my conversion of milliliters to liters, is in the blue applies to both. So there you go. That's what I know about the lead, that's what I know about the chloride, so that's fine because I can substitute straight away, and that's what I know about both, and I've converted to liters. So I now have to get a concentration of lead ions. And the only way I can do that is first working out the moles, the amounts of mass divided by molar mass, and again use your units, grams divided by grams per mole. The grams will cancel, and I'll have a final unit of mole. And then C is equal to N over V. The N is on top because moles over liter will give you a unit of moles per liter. So use units the whole time, even here when you're substituting. If you're not sure if you're multiplying or dividing, use your units and see if they cancel. So now I've got my two concentrations. Now I just say RP, plug in the orange value for the lead, the green value for the chloride. Now remember, we still have to square it because I've got 2 chlorides. Do I double it over here? Because remember in the past I'd say, remember x gets doubled and squared. So do I double it here? I was given it as 0.4. Is the... Okay, no answer. We don't double here, because the chloride is coming from the seawater. So, Catherine, you're correct. We do not double. The chloride's coming from the seawater. It's not coming from the lead chloride. So, that 2 there doesn't mean we've now suddenly got double the amount of... We don't have 0.88 anymore, because it's coming from the seawater. Can you see it's a separate source of chloride? So I don't double the chloride because the chloride's from the seawater and not from the lead chloride. Because remember that assumption, we always ignore that extra X. I haven't done that ICE method, but you could. In the book, I've got that ICE method all the way pretty much. But I do square it because my IP expression does have that. Remember, it's lead times chloride times chloride. And now I get that value. And now before I click on, can you tell me, is my IP bigger or smaller than my KS? Bigger, correct. So will I get a precipitate being formed or not? So yes, precipitate. No, no precipitate. Yes, because again, if this is bigger than that. The only way I can make this smaller to match the Ks is if I've got fewer lead and chloride ions, which means it's got to go to the left. So I'm going to get more lead chloride being formed, so I've got to precipitate. Now you must always write that statement, particularly for excellence. You may get away with it with achieved, I'm not too sure, but I know for excellence, if you don't have that final statement, then you don't get excellence. Because it says determine whether a precipitate will form, you have to answer the question. So you've got to say a precipitate will form. Don't leave it up to the examiner to think, oh, now did he know that RP is bigger and therefore I'm going to get a precipitate? So make sure you do that final step. Right, here's another one where I'm now again mixing two solutions, a lead nitrate solution with a calcium chloride solution. So there's my Ks for lead chloride. So if you've got a Ks value given, you know the insoluble salt you're working with is lead chloride. So, you know, that's the equation you write. Now the cation and anion are from two different sources, like I had the previous one where I had seawater for the chloride, and I had, actually I can't even remember the question anymore, but I think it was also lead coming from a different place. So here it's the same thing. I've got lead nitrate, my lead ions are coming from one solution, and my chloride ions are coming from another solution. So first the equation, then the expression, and then you list things. And we know which equation to write because we've either know our solubility rules or we've looked for the Ks. Okay, then you link them. So it's, don't try and take shortcuts with this. So we know what both is, we know what relates to the lead, and we know, okay, so I've done it actually slightly differently. What's in green is chloride, but I've decided to work out the lead first. If I mix a 50 ml solution with a 50 ml solution, or say I've got this lead nitrate solution and I add 50 ml of water, have I diluted my lead nitrate? Not too sure? So, yes, I have, because I've added water to it. Now, if I add any other solution to it that doesn't contain that lead or nitrate, well, lead's the one we're interested in, can you see if I add any other solution, I am still diluting it because I've given it a bigger volume. I've added together 200 mils with 300 mils, so now my beaker is half a litre. So I've diluted it. So I can't just say, there's my concentration of lead, put that in. There's my concentration of chloride, put that in. Go for it. You're going to be wrong. Yep. Andrew, you can do things like there's lots of little shortcut methods, so you can use. I'm just sort of plugging the sort of step-by-step way, but there are lots of shortcuts. So I can't just say my lead is 2.5 times 10 to the minus 4 because I've diluted it now by adding it to the calcium chloride solution. So my volume is now not 200 mils anymore, it's 500 mils. So converting to liters, it's 0.2 divided by 0.5, and that is actually my new concentration of my lead ions now that I've added it to the calcium chloride solution. Can you see it's diluted? I had 2.5 times 10 to the minus 4, now it's 1 times 10 to the minus 4, less concentrated. Chloride's exactly the same, I've diluted it. So I take the concentration I had, times it by the 300 moles I had, but now I've got 500 in total, so you divide it by the 500, or can you see I've converted it to liters. You didn't have to convert to liters in this case because the milliliters here would have cancelled out with the milliliters there, so you could have said 300 divided by 500, but it's perhaps a good habit to always convert milliliters to liters. It's or just have units all the time so you know when you can cancel out and when you can't. So there are my two new concentrations, and now I just take the RP, plug in the new concentration of lead, the new concentration of chloride, and there I get my value, and I check, is it bigger or smaller? So is this value bigger or smaller? So is the RP bigger? It's smaller. So 10 to the minus 10 is smaller than 10 to the minus 5. Don't be confused. Don't look at the 3.2 and say, oh, 3.2 is bigger than 1.7. So this is important because that gives you all the placeholders. This is just 0.00001. This is 0.00000000003. So there's a lot more zeros there. So this is definitely smaller. Because it's smaller, I won't get a precipitate being formed. So what's going to happen here, more will dissolve. If this is too small an amount, I've got to reach equilibrium, I've got to get more and more to dissolve. So if I mix those two solutions, I'm not going to get a precipitate. Any questions? No. Okay. Right. Now, I see that we got 5 minutes left, so let's go very quickly. We've looked at common ions, complex ions. Complex ions you have to learn off by heart, and they're definitely there for excellence. Okay? They're not necessary for achieve, but if, say, you stuffed up an achieved question, then if you know something about complex ions, you can, you know, still pass. And the other one that I'm not going to deal much about is the pH. That we'll do in the next lesson. I'm just wondering should I carry, well, I'll just do this so that when we go over it next time, I'm going to say meet Zach and Zelp. So next time, remember Zach and Zelp, and they will help you remember what the complex ions are. So Zach is the one that forms complex ions with ammonia, and Zelp is the one that forms complex ions with hydroxide. Now, what we mean by complex ions is, say we've got a salt, and these hydroxides or ammonia can actually, just like water, dissolve the copper ion or whatever it is. These can do it in exactly the same way. So it's got the lone pairs that it can surround it, and it forms actually a complex ion. Now, ammonia forms complex ions with zinc, silver, and copper. That's where the Zach comes from. And I've made Zach blue because ammonia, I hope you know, is not as strong a base as hydroxide. Zelp, he is for complex ions with hydroxide. So zinc, so remember zinc fits in both, forms 2 lots of complex ions. Not silver, so that's why I put an L in there, the Zelp, for the aluminium, okay? And the L is also to remember the lead, because if you think of PB, you might not think of lead. So if you think of Zelp, that L stands for the aluminium part as well as for the lead, and the P is helping you to remember it's a lead. So, and then another trick is that all complexes that you have to know have 4 ligands. So in other words, that number over here would be 4, except for silver, which only has 2. As you can see, there's only 2 there. Okay. Right, I think I'm going to stop there, and I will go over the complex ions, I think, next week as well. And what I want to start doing next week is, because Science Scribe has done lots of good examples, I'll finish this, and then we're going to start doing just going more over past papers. I'll write an email where I'll say, see if you can watch a Science Scribe video, and then we're going to do much more problem solving rather than explaining. Or do you prefer me doing the explaining and you doing the problem solving on your own? So Catherine and Andrew, what do you prefer? Lessons like this where I do explaining, or would you prefer more problem solving? more problem solving. Okay, so I'll send them my next email. I'll say, fine, well, we'll do this still. And then I'll say, look at these Science Scribe videos. And then we'll, at least half the lesson next week, we'll be going over past paper type things so that we can get more practice with answering questions. So I'll see you next week. Right. Okay. Bye.